Now I'm going to show you how to get the pH, the actual pH value for a titration. And I'm going over the calculations just for a weak acid titrated with a strong base. I just copy my graph, the same plot that you have previously, and I erase the numbers because we're actually going to determine an actual number for the pH values in your graph. So I added 4 points here, 1, 2, 3, and 4. Point number 1 represents the pH value before any base is added into your acidic sample. So you have your weak acid and we're adding the base. So that number 1 represents the pH of your weak acid with nothing else in there. Number 3, and then I'll go back to number 2. Number 3 represents the pH value at the equivalence point. Whatever number it is, it's a number above 7. And before doing anything in your calculations, you should keep that in mind. Look, you have a weak acid. That initial pH that you're calculating should be a number between 2 and 3.5. Number 3 represents the pH at the equivalence point, and that number, since you have a strong base and that's what you're using to titrate a weak acid, that pH value that we're calculating in number 3, it has to be a number above 7. Number 2, now we're going back to number 2. That number 2 represents the pH value at halfway the equivalence point. So I have my number 3, and you see how I have a dashed line going down to your x-axis where you have volume of base. That volume of base that I have marked right there represents the volume of base that you need to add to neutralize all of the acid present. That's the equivalence point. That volume divided by 2 will tell you the volume that you need to neutralize half of the amount of acid present in your solution, which is your halfway the equivalence point. So that number 2 is where we're calculating the pH at halfway the equivalence point. And then number 4, that number 4 represents the pH after the equivalence point. So we can choose any volume after we know how much we need to reach the equivalence point. Any volume after that number that you have for the added base at the equivalence point will be represented by number 4. Anything after the equivalence point. We have here a problem where we have to solve different parts. So in your problem, you're given a volume and a concentration, 20 milliliters and 0.1 molar. That volume and that concentration corresponds to a volume and a concentration for your weak acid HA, a generic formula. We're also given a concentration of sodium hydroxide. So you have a titration, your sample, the analyte, it's 20 milliliters of your weak acid HA with a concentration of 0.1. The titrant, it's sodium hydroxide with a concentration equal to 0.125 molar. You're also given the value of your equilibrium constant for the weak acid HA. And the first thing that we have to calculate is the volume of added base, so sodium hydroxide, that we need in order for your titration to reach the equivalence point. So a couple of things. Equivalence point, it's where the concentration of your acid equals the concentration of the base. And I'm writing just the hydroxide because the sodium hydroxide, that's the base that you're adding, and the base will react with the acid. So the base, the part that reacts with the acid, is not the Na, it will be the hydroxide ion. So at the equivalence point, you have the same concentration of acid and base, which means that all the acid is being neutralized. Now to calculate a volume, and you need a volume for NaOH, that's what we want. If you have your equation for molarity, molar concentration is the moles of your solute over liters, a volume. You're trying to calculate a volume here. So to calculate a volume, you can solve this equation moles over molarity, which means that if you want to find out liters of NaOH, that's what you want. A volume of the base that you need in order for your titration to reach the equivalence point. So the liters of sodium hydroxide that you need the moles of sodium hydroxide divided by the molarity of sodium hydroxide. In your problem, you're given that number. Molarity for sodium hydroxide is 0.125 molar. So in order for you to find out that volume of sodium hydroxide, you're still missing the number of moles of sodium hydroxide. But in this problem, you have enough information for you to find out the number of moles of sodium hydroxide. If you check the information that you have for the acid, you have a volume and you have a concentration. Still using the same equation for molarity, moles over liters. So if you solve your equation of molarity for number of moles, you have molarity times liters. So you can get moles if you have a concentration and a volume. You don't have a volume for sodium hydroxide. You do have a concentration, but you don't have a volume. But for your acid, for the acid, you do have a volume and you do have a concentration. So you can actually calculate the moles of the acid if you have the molarity of your acid and the volume of the acid, which you do. So the molarity of your acid is 0.100 and the volume is 20 milliliters, but you need that volume in liters. So 20 divided by 1,000, that will give you 0.02. And that should be liters. So when you do your molarity times your volume in liters, and both numbers corresponds to the acid, concentration of your acid, volume of the acid, that will give you the number of moles of the acid, which is 0.002. Now we know that at the equivalence point, the number of moles, right, of the acid, it's equal to the number of moles of the base. You need the same number of moles of base in your reaction to neutralize that number of moles of the acid that you have initially. So you're starting your reaction with 0.002 moles of the acid. That's what you have in your Erlenmeyer flask. If you're adding 20 milliliters of HA, with a concentration of 0.1. In those 20 milliliters, what you have is 0.002 moles of HA. So to reach the equivalence point in your titration, you need 0.002 moles of your sodium hydroxide because the reaction is 1-to-1, which means that that number is the same number of moles that you need to plug in your equation of here. Remember, you're trying to calculate the volume of sodium hydroxide that you need to reach the equivalence point. So to calculate a volume, you need moles and molarity. For sodium hydroxide, you have the molarity, but you didn't have the number of moles. So we're using the number of moles of the acid in your sample to actually get the number of moles of the base that you need to reach the equivalence point. So now to get that volume, we're doing the moles of hydroxide divided by the concentration. So this concentration here is moles per liter, which means that your moles is canceling out that unit and you're getting a number that it's in liters. So you can do the calculator 0.002 divided by, and that will give you 0.016 liters, which is the same as 16 milliliters. So what that volume is telling you, okay, when you're titrating your 20 milliliters of your weak acid with a concentration of 0.1, what you have is 0.002 moles of the acid in your sample. To reach the equivalence point in your titration, you need to use 16 milliliters of that solution of sodium hydroxide with a concentration of 0.125 molar. That volume, 16 milliliters of that solution with a concentration of 0.125, that volume and that concentration contains 0.002 moles of sodium hydroxide, which is the amount of moles that you need to neutralize the number of moles that you have in your sample. Still working on the same problem. I have the problem again here, but this is just letter B of the same problem. We still have the same volume on your sample, the same concentration for the acid, same concentration for the sodium hydroxide. So the second thing that we have to calculate, we're trying to calculate the pH of your sample. Okay? So the pH of your sample after adding different volumes of sodium hydroxide. The first thing that we calculated was how much sodium hydroxide you need to add to your sample to neutralize all of your acid, reaching the equivalence point. So we have 16 milliliters. Now letter B and letter C and letter D, what we're trying to find out is a pH value. pH values in your titration curve. The first one is the pH value for your weak acid, which is the pH value before adding any sodium hydroxide. It's like you have your 20 milliliters of your weak acid HA with a concentration of 0.1 in your flask, and you're measuring the pH for just that sample without adding any base. This is a calculation that you know how to do because This is a calculation of pH of a weak acid in water. It's just the dissociation of your weak acid in water. And we use the equilibrium constant to find out concentration of hydronium in water. And from there, we calculate the pH value. So we're trying to get this first number here. That's my number 1, which is my first pH value here. So I'm going to write down my equation for the dissociation of your weak acid, which is HA. So you have your acid in water. It's the acid, which means that it will be transferring the proton to the water molecule, which is acting as the base in this example. So you're forming your hydronium ion H3O plus and your conjugate base, which is the negative part of your acid. The acid molecule is losing the proton, which is the positive part, and it's forming your conjugate base, which is the negative part. And I'm writing down my equilibrium constant expression. Hydronium, concentration of the conjugate over the concentration of HA. So you have the value of your equilibrium constant right there in your problem, 1.8 times 10 to the minus 5. So we solve this just using the ice table because we're trying to find out a pH value. So pH is minus log of the concentration of hydronium. So you need to find how much is the concentration of hydronium in this equilibrium, so you can plug in that number in your equation for pH and you can calculate the pH value. So we have initial concentration for the weak acid, it's given, that's 0.100. Initial concentration for the ions, that's 0 because you're getting those from the dissociation of your weak acid. Now we move to the change, and the initial concentration of your weak acid will be decreasing by X amount, and the concentration of your ions on the product side will be increasing by X. So we have that this is X0 plus X, which is giving you X for hydronium, 0 plus X, which is just giving you X for your conjugate base. And then for the acid, we have 0.1 minus X as the equilibrium concentration. But we can use the simplification, assuming that the X value is so small that that initial concentration is not going to change by a lot. And we can assume that because the value of your Ka is 1.8 times 10 to the minus 5. So we can use the assumption of the X value as a small number. Insignificant change in your initial concentration whenever the Ka value or any equilibrium constant value is 10 to the minus 4 or smaller than that. So instead of just writing here 0.1 minus X, I'm going to go ahead and just write down your 0.1, which means that you can plug in that in here, and that will give you X squared over 0.1. X squared because hydronium is X, your conjugate base is also X here, so that will be X times X, X squared. And then you have your initial concentration, which is the same as the concentration at equilibrium whenever the Ka value is 10 to the minus 4 or smaller than that. So I'm going to move this here because I don't have enough space in there. So your Ka equals X squared over 0.1. Ka is 1.8 times 10 to the minus 5. X squared over 0.100. So now you do 1.8, I'm solving for X, so 1.8 times 10 to the minus 5 times 0.100, that will be X squared. And then we do the square root of that number, and that will give you the value of x. So I have 1.8 to the minus 5 times 0.1 square root of that number. So x will be a number close to 1.3 times 10 to the minus 3. So I'm going to put the x value is the same as concentration of hydronium from your ice table. You can see that at equilibrium the concentration of hydronium is x. So what you're solving here is the x value, which is 0.0013 or 1.3 times 10 to the minus 3. That x value is the concentration of hydronium. So you can actually calculate the pH because you already have what you need to get the pH value. Minus log of H3O plus and I'm going to round that number to two significant figures, and that will be like something close to 2.9, and that's your initial pH value, which means that here in my graph, before adding any base to my sample, that number 1 right there has a pH value equal to 2.9. In letter C, we're going to calculate the pH at halfway the equivalence point. So in letter A, we calculated the volume of sodium hydroxide that we need to reach the equivalence point, 16 milliliters. So when you are at 16 milliliters, all of the acid is being neutralized by the base that you're adding. You have the same number of moles of acid and base, and all of the acid has been neutralized. Now, halfway the equivalence point, if you need 16 milliliters to neutralize all of your 0.002 moles of your weak acid, you need 8 milliliters to neutralize 0.001 moles of the acid, which is half of the total number of moles of acid that you need. So in my graph, I label number 1, which is the initial pH of your solution before adding any base, and we calculated that 2.9. Now we're going to calculate the pH after adding 8 milliliters of sodium hydroxide, which is the volume that you need to neutralize half of the acid that you have in your solution. Now this calculation here is very easy. I'm going to show you how to get the pH, and then I will explain why this is the pH at halfway the equivalence point. At halfway the equivalence point, you have a region in your titration where you have a buffer solution. Every time that you neutralize a mole of the acid, you're forming 1 mole of the conjugate base. And remember, for you to have a buffer, you need a mixture, your weak acid, and something that is forming that conjugate base in solution. The shape on your graph is actually telling you that you have a part right there where you're forming a buffer because the pH remains almost constant. If you do a titration in that part where you have your number 2 here in your graph, your pH value will be changing by a small amount, maybe by 0.1, 0.01. Sometimes you get the same value twice. You're adding the base and you keep adding the same value of pH because you have a buffer solution. Since it's a buffer, I'm going to use an equation that you know. It's the Henderson-Hasselbalch equation. But to calculate the pH at that halfway the equivalence point, you have a very simplified version of your equation. The pH at halfway the equivalence point is going to be equal to your pKa. You know that your Henderson-Hasselbalch equation is pKa plus the log of the concentration of your conjugate base over the concentration of the acid. So we don't have that part in the equation. pH equals to pKa, and you can calculate the pH because your pKa, look, you have your Ka value, which is 1.8 times 10 to the minus 5. And pKa, it's equal to minus log of Ka. So pKa here, it's going to be, let me do minus log of 1.8 to the minus 5 for 0.74. Since pH equals pKa, the pH at halfway the equivalence point is equal to 4.74. So in your graph, that number 2 corresponds to a pH value that is equal to 4.74. Now I'm going to show you with a simplified representation what is happening here. You have your acid HA, and you know that we have 0.002 moles of the acid in the sample. That's what you have. You calculated that number doing concentration times volume in liters, you get the number of moles. So what I'm doing here, it's something like a generic thing. I have my acid, and I'm going to say that I have 4 moles of the acid. That's not correct. I want to do with the hydroxide. So I have 4 moles of the acid in my sample. If you have 4 moles of the acid in the sample, to neutralize 4 moles of the acid, you need 4 moles of hydroxide. Okay? So at the equivalence point, you need to have 4 moles of the acid, 4 moles of the hydroxide, and all of the acid is going to be neutralized by the hydroxide. Now at halfway the equivalence point, you're neutralizing half of the acid. So out of your 4 moles of the acid, at halfway the equivalence point, you're neutralizing only 2 of them. So you're getting water because the H, the proton, right? That's an acid-base reaction. The proton reacts with your hydroxide to give you a water molecule. So the other thing that you're getting right there is the conjugate base of your acid. And that's happening with 2 moles because you have a total of 4 and you're not at the equivalence point, you're at halfway the equivalence point where half of the total number of moles of the acid is being neutralized. So I have a second one, which is also giving you a water molecule plus a mole of the conjugate base. For every mole of the acid that is being neutralized, you're forming 1 mole of the conjugate base. So this is how your halfway the equivalence point is going to look like. Your initial number of moles of the acid in my representation here, it's 4 moles. At halfway the equivalence point, you're neutralizing only 2 moles of the acid. So you can actually see that you have 2 moles of the conjugate base right there, because you're neutralizing out of your total number of 4, you're neutralizing 2 of them. So you're forming 2 moles of the conjugate base, because for every mole of the acid that you neutralize, you're getting 1 mole of the conjugate base. And you have right there left, out of your total number of moles of 4, you're neutralizing 2 of them, so you have 2 of them left. So the number of moles that you have in your flask at this point for the conjugate base and the acid is the same amount. So this is your equation, the Henderson-Hasselbalch equation. The conjugate base here, it's A minus. The acid is your HA. At halfway the equivalence point, the number that you have for the conjugate base is the same as what you have for the acid, which means that the concentration is the same, because concentration is moles over liters, right? That's molar concentration, but the total volume is the same for both of them. So the concentration of your conjugate base and the concentration of the acid is going to be exactly the same, which means that that is going to give you 1. The log of 1 is equal to 0. And that's how we get that at halfway the equivalence point, the pH equals the pKa. And that's always true. So the calculation for your pH at halfway the equivalence point is very simple. If you have the value of the Ka, you need to calculate your pKa minus log of your Ka. That will give you the number for your pKa, and that's the same number that you need for the pH value. And that is correct, because at halfway the equivalence point, the concentration that you have left for the acid is equal to the concentration of the conjugate base that you're forming. Since those two concentrations are the same, you're going to get a ratio of 1 in your Henderson-Hasselbalch equation. The log of 1 is 0, and that's how we get the simplification for that equation. So in this part of the problem, still the same problem with your initial volume of the acid, initial concentration. We're going to calculate the pH at the equivalence point. So we have your initial pH for the weak acid. We calculated that, 2.9. We calculated the pH at halfway the equivalence point, which is equal to the pKa, 4.74. And you see that the pH is increasing because we're adding sodium hydroxide. You start with an acidic pH, and then as you keep adding the sodium hydroxide in your titration, that pH value will be increasing. So we're calculating the pH at the equivalence point, and at the equivalence point, all of the acid is being neutralized. So remember, you calculated the number of the moles of the acid that you have in your sample. Volume in liters times concentration will give you the number of moles of acid in your sample, which was 0.002. At the equivalence point, all of the acid is neutralized. I'm showing you here the neutralization reaction. You have the molecule of the acid HA. It's reacting with the hydroxide that you're adding from the burette. So when you have your hydroxide and the acid, the proton is transferred to the hydroxide to give you a molecule of water. And so you're forming H2O from the reaction between the hydroxide and the proton in your acid. Every mole of the acid that you're forming is giving you a mole of the conjugate base. You see your acid is HA, so if the acid is losing the proton because it's being transferred to the hydroxide to form the water molecule, what you have left is the conjugate base of your acid, A minus. So if you start with 0.002 moles of the acid, at the equivalence point, you don't have more acid because the acid is being neutralized by the base entirely. So what you have now is just the conjugate base and water. So at the equivalence point, my chemical species that are present in my flask is the conjugate base and the water. Okay? Now, the conjugate base, it's a base, which means that it can accept a proton from the water to give you that. You see how this HA that I'm writing here and this hydroxide that I'm writing here, the HA is not from your initial concentration of the acid. That acid, all of those molecules were neutralized. The hydroxide is not from the sodium hydroxide that you're adding in your titration. These two here, they're being formed when the conjugate base reacts with the water that you have in your flask. So now what you have in the flask is just the conjugate base because all of your acid was neutralized, giving you the conjugate base and the water, but you still can have a reaction between them, giving you a very small amount of the acid molecules and the hydroxide ion. Now, if we want to calculate the pH at the equivalence point, we're starting with our equation here. And I'm going to prepare an ice table. This here, you don't have hydronium form in your equilibrium. You have hydroxide, which means that if it's hydroxide, what we need it's Kb. Kb expression, okay? You're forming a hydroxide. You have your conjugate base in the water giving you back the acid and the hydroxide. So your Kb expression is your products over the reactant, which is just the conjugate base because that's water and we don't need that. You don't have a value of Kb given. You have a value of Ka right there. But we can calculate a value of Kb, which you're going to be needing to solve this problem. So Kw is equal to Ka times Kb, which means that Kb is equal to Kw divided by Ka. Kw is 1.0 times 10 to the minus 14, and you have your Ka value, which is 1.8. So you can calculate the Kb value. Now this is a dissociation equation. You have the conjugate base reacting with the water to give you your products of the weak acid molecule and the hydroxide ion. Now we need an initial concentration of that conjugate base, right? we need a number right here, how much of the conjugate base I'm starting with, and from that conjugate base, how much is actually being converted to your products, which is the molecule of your weak acid and the hydroxide ion. So to find out that initial concentration of your conjugate base, concentration is moles per liter. Okay. Now remember, for every mole of the acid that you have in your flask that it's been neutralizing, you are getting 1 mole of the conjugate base. You can see that in the neutralization reaction. HA plus hydroxide is giving you 1 mole of the conjugate base and 1 molecule of water. So if you start this reaction with 0.002 moles of the acid, when all of your 0.002 moles of the acid are neutralized, you're getting 0.002 moles of the conjugate base, which means that to get a concentration of the conjugate base, you need the moles of the conjugate base divided by a total volume. The moles of the conjugate base are equal to the moles of the acid that you have, 0.002 moles. The total volume here, you can calculate. You're starting this reaction with 20 milliliters of the acid, and to reach the equivalence point, which is where we are right now, you need to add 16 milliliters of sodium hydroxide. That's the first thing that we calculated. How many milliliters of sodium hydroxide with a concentration of 0.125 you need to reach the equivalence point. And we calculated that as a 16. Okay? So your total volume right there is 36 milliliters, but this is a molar concentration, which means that you're not looking at your number in milliliters, you need liters. So 36 milliliters is the same as 0.036 liters. So that's moles per liter. And that will give you how much or what's the concentration of that conjugate base in your flask at the equivalence point. So you do 0.002 divided by 0.036, and that's 0.56. Okay? That's your initial concentration for the conjugate base. That number right there, I'm going to write down right here to solve my ice table, so we can find out the value of X to calculate pOH. That's what we're doing. So I have my initial concentration for the conjugate base. The water, you don't need that. Initial concentration for your products, you're forming them, so that's 0 minus X plus X. 0.056 minus X, you will get a value of Kb here. It's 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. That will be a small number, 5.6 times 10 to the minus 10. A small number for Kb, which means that your initial concentration will be the same as your concentration at equilibrium. So now I'm going to plug in numbers in my Kb so I can calculate how much is X. Times 10 to the minus 10 equals, you see how you have HA times OH minus your acid times the concentration of hydroxide, so that will be X squared over 0.056. So we can solve for x, which is going to be the square root of 5.6 times 10 to the minus 10 times 0.056. So I have square root 5.6 to the minus 10 times 0.056 5.6 times 10 to the minus 6. That's the value of x. What the value of x is telling you is the concentration of hydroxide. At the equivalence point, you're getting hydroxide as a product, not hydronium. So you're using a Kb because what you have is something basic. This is the equivalence point of a weak acid titrated with a strong base. When you have a titration between a weak acid and a strong base, the pH at the equivalence point will be higher than 7, which is a basic or alkaline pH. So you're getting your value of X, which is the same as the concentration of hydroxide. So you can calculate the pOH value, which is minus log of 5.6 10 to the minus 6. 5.25, I'm going to round that to two significant figures, 5.3. And to get the pH, we're going to do 14 minus 5.3, 8.7. So that's the pH at your equivalence point. So there's a lot of things that you need to calculate to find out that pH value at the equivalence point for this specific titration. I have prepared a summary of the steps that you need to follow or the things that you need to calculate. You don't have to follow these steps in that specific order. So to summarize all the things that we have to do in order for us to be able to calculate that pH in your titration where you reach the equivalence point, I have prepared a list. You don't have to follow the steps in the same order that I have them here. So number one, you need to remember that for every mole of the acid that you're neutralizing, you're getting a mole of the conjugate base. So that number, initial number of moles of the acid, which you're calculating because you're given a concentration, molar concentration for the acid and a volume for the acid. You can calculate moles because molarity times volume in liters will give you the number of moles. So you can calculate the moles of the acid, and that's the same number of moles of conjugate base that you will have at the equivalence point. So you're using that number of moles of your conjugate base at the equivalence point to find out that initial concentration of the conjugate base that you have in your equivalence point. So you have the number of moles, and that number of moles divided by a total volume in liters will give you the molar concentration. Now to get that total number of moles, total volume, in liters, we have the volume of your sample of acid, which in this example was 20 milliliters, and then the volume of the base that you need to add to your sample to reach the equivalence point, which is what we calculated in letter A. You calculated that to reach the equivalence point, where you have the same number of moles of acid and hydroxide, you needed 16 milliliters. So the total volume is your initial volume for your sample plus how much sodium hydroxide you need to add to your sample to reach the equivalence point. That total number will be in milliliters, so you have to convert that number to liters. So you can calculate a concentration of that conjugate base at the equivalence point. The moles of your conjugate base divided by the total volume in liters will give you a molar concentration. So you need that number to use in the ICE table later. Another thing that you have to do, if you're not given the Kb value to solve your ICE table, you can calculate the Kb value. Kw is Ka times Kb. Kw at room temperature has a value equals to 1 times 10 to the minus 14. So if you're given the Ka for the acid, which you will have, you can use the Ka value and the Kw to find out the Kb that you need to solve the ICE table for your pH value at the equivalence point. So Kb is equal to your Kw divided by the Ka value that you're given. Now you have to set up your ICE table. The equation that you have, all of your acid is neutralized to give you the conjugate base and water. Every mole of the acid that you're neutralizing is giving you 1 mole of water and 1 mole of the conjugate base. So at the equivalence point, that's what you have in your flask, conjugate base and water. But the conjugate base, it's a base, which means that it can accept a proton from the water molecule. So you have your conjugate base plus the water in your container, in your flask, at the equivalence point. If the water donates a proton to your conjugate base, you're forming again the molecule of your weak acid, HA, and hydroxide. Now remember, this equilibrium, what you have on the product side is a super small amount of those ions. They're coming from the dissociation of what you have on the reactant side. So you have your ICE table now. You need to put your number, your numerical value for the initial concentration of your conjugate base, which I'm showing you how to calculate in step number 2. You can cross out the water because that's a pure liquid that you don't include in your equilibrium constant expression. You have your initial concentrations for your product species at 0. The change is X, which is what is being formed during your equilibrium. And then at equilibrium, right, the 0 plus X, that's giving you X. If you look at your Kb expression, you have HA times hydroxide over the initial concentration of your conjugate base. So you have a numerical value that you can plug in as the initial concentration of your conjugate base. And then for HA and OH minus, that's X. So you simplify your Kb expression as X squared over your initial concentration of the conjugate base. You're solving for X because you have a number for Kb, you have a number for your initial concentration of the conjugate base in your flask, on your Erlenmeyer flask at the equivalence point. You're solving for X. The value of X is telling you the concentration of hydroxide in your reaction. With the concentration of hydroxide, what you can calculate is the pOH. So you're solving your ICE table to get how much is X, so you can get the pOH, and then with that value you can calculate the pH.